This question is about a system in equilibrium in which you see that the load is hanging with the cords, and it is hanging from the ceiling of an elevator. All right, and important thing is that it is moving with constant velocity. All right, that's why I said system in equilibrium, because this whole system is moving at a constant speed, constant velocity. It means that it is the dynamic equilibrium. All right, which means that acceleration is zero, and sum of all forces exerted inside a system is zero. All the forces are balanced. So in this question, you have to find out the tensions in each string. So which tensions, like T1, T2, and T3. All right. So what will be our strategy to solve the question? Remember, first of all, we will draw free body diagram, and from that we will make equation. With the help of equations, simultaneously solving them will give us ultimately our answers. Okay, so let's start from the free body diagram of this load. So students, if we are drawing its free body diagram, so we will draw all the forces exerted on this. So here is its free body diagram, and we are considering this is the load. So as we have already seen that it is moving with constant velocity, the whole system, which means all the forces are balanced. So as you see in this diagram, this is a force that is applied on this load, and it is written in this diagram as T3, the tension in this third chord. Okay, whereas which force is balancing it? The force, the which one is balancing, is mg. All right, so with the help of this, I told you that we will make equation, and there's a no force along x-axis, so sum of all forces along y-axis must be balanced. So we must say that T3 minus mg is 0, which means that the T3 is equals to mg. Do we know the mass? That is 5 into 9.8 must be equals to the value of this tension. So that is 49 Newton is the force exerted on this. All right, now our next is the free body diagram of this knot. Okay, this knot, where we see that there are three forces. Let me show you all in the free body diagram. So at the knot, we see that there are three forces which are exerted. The one is T2, and don't you think that the T2 must be more than T1, because this string is more stretched? That's why. And finally you will see that the T2 will be larger. All right, so that's why when I will draw its arrow in a free body diagram, I will draw a longer arrow like this. Now the next force must be at an angle of 40. All right, from the diagram we can see, and I will draw its smaller arrow. So this is the T1 according to the question, and the sum of these two forces are balanced by T3. All right, so don't you think that this T3, all right, so when I will draw it here, so I have to draw its longest arrow, or just symbolically showing you that T3 is in fact more than all of the other forces. All right, so this is the free body diagram. Okay students, now the next diagram will help us to make equations. All right, we know sum of all forces equals to 0, and so let us analyze it now logically here, that this angle is 50 degrees. All right, so when you will make its component, okay, right, don't you think that when you will make its component, this one is a x component, so this must be T2 cos 50 degrees. All right, and this component towards x-axis, positive x-axis, is balanced by its x component, which is T1 cos 40 degrees, whereas the other component is T1 sine 40, and this one is T2 sine 50 degrees. Okay students, so we have seen in detail that what equation do we get from the second diagram, that the T2 cos 50 towards the positive x-axis is equals to T1 cos 40 decrease. Okay, well, in fact, we can get the value t2 over t1. We can also write it like this: cos 40 over cos 50 decrease. Okay, which in fact gives us this ratio is equals to 1.19. Okay, and I told you in the start that the t2 is more than t1 because this string is stretched more conceptually, right? That's why the tension must be larger in this string. Okay, now let's write equation for the y-axis. So students, as you see from the diagram, the t1 sine 40 degrees directed upward, vertically upward, plus t2 sine 50 degrees is also vertically upward is equals to t3. Okay, so now we get an equation. In this question we want to find all the values of tensions. We already know the value of t3, that is 49, whereas in this algebraic equation, don't you think if we plug the value of t2, which is 1.19 t1, let us put the value. Sine 40 is 0.64 t1 plus the value of t2 is 1.19 into sine 50 is equals to 49. So it is 0.64 t1 tension in a chord 1 plus this is giving us in calculator it is 0.91. Okay, 0.91 is equals to 49. You can take it on the other side. So 0.64 t1 is equals to 48.09 newtons. Okay, and if we find finally the value of the tension t1 must be equals to sine 40 is 0.64, so 0.64 t1 plus, can I plug the value of t2 here? So it will be what it should be. So it should be 1.19 t1 into sine 50 degrees is equals to 49. Okay, so we have to just simply solve this algebraic equation, and you see here this is 1.19 and sine 50, if you multiply it, it will become 0.91. Okay, 0.91 t1, and here we have already 0.64 t1 is equals to 49. So 1.55 t1 should be equals to 49. So finally the value of the tension in a chord 1 is equals to 31.61 newton. Okay, this is a force that is actually in this direction. You see in this diagram 31.61 newton. All right, now can you, if you put the value here, you can find directly t2. Okay, so what should be the t2? T2 must be equals to 1.19 into T1, and if we plug the value which is 31.61, so 37.61 Newton is the force in the second chord. Alright, and finally these are the values, and this is 49 Newton. So you remember I told you that as it is moving with a constant velocity, that's why we are saying this is in equilibrium. And you can also indirectly prove it if you add these three vectors by the head to tail rule. You will see they will end up making a closed polygon. Let me show you that very quickly. This was a tension T1 and the tension T2 was at an angle 50 degrees. So if I draw this arrow, look at this arrow like this. So this T2, right? And you remember where was the T3? T3 was vertically downward. So this is making closed loop, right? That's why it is in equilibrium. It has been proved once again.